Good afternoon, everyone. Today I'll be presenting my work on benchmark construction and evaluation metrics for breast cancer prognosis prediction. This assignment explores how we can use machine learning to predict patient outcomes using both genomic and clinical data. The presentation will cover four main problems: data preparation and model training, optimal threshold selection, precision recall analysis, and the concordance index for survival analysis. Here is our roadmap for today. We'll start with benchmark construction, where I trained four different machine learning models. Then we'll discuss threshold optimization for clinical decision making, followed by precision recall curve analysis and failure analysis. Finally, we'll explore the concordance index and its relationship to AUROC in survival analysis context. Our dataset combines genomic and clinical information from 465 breast cancer patients. The genomic data includes 20 gene expression features, while clinical data captures 10 important variables like age, tumor size, and treatment information. The dataset is relatively balanced, with about 47 good prognosis and 53% poor prognosis cases. We use stratified splitting to maintain this distribution in both training and validation sets, which is crucial for unbiased model evaluation. The combination of genomic and clinical features allows us to capture both the biological characteristics of the tumor and the patient-specific clinical factors. The class distribution shows our dataset is well balanced, with only a slight preference toward the poor prognosis class. The imbalance rate of 0.52 is very close to 0.5, which means we don't need special technique like AMOTE or class weighting. More importantly, the stratified split successfully maintained similar proportions in both training and validation set. This ensures that our model evaluation will be reliable and not biased by different class distributions. A balanced dataset is particularly important in medical applications when we want to avoid models that simply predict the majority class. I trained four diverse machine learning models to create a comprehensive benchmarks. All models successfully exceeded the required validation AUROC of 0.73. This SVM with RBF kernel performed best at 0.7567, followed closely by random forest at 0.748. The neural network achieved 0.7418 with a three-layer architecture. An important technical note: feature set standardization was absolutely critical for the convergence of logistic regression, SVM, and neural network. Random forest doesn't require this, as it's based on decision trees, which are invariant to feature scaling. The similar performance across different model types suggests that the signal in the data is relatively strong and can be captured by various algorithms. For the rest of the analysis, I'll focus on the neural network as it provides a good balance of performance and interpretability through probability outputs. Threshold selection is crucial in clinical applications. I evaluated two common approaches: F1 score maximization and Youngdan's index. The F1 score optimal threshold of 0.35 is quite low, which would result in high sensitivity but many false positivities. For breast cancer prognosis, while we don't want to miss high-risk patients, we also need to consider the cost of overtreatment. Youngdan's index finds the threshold that maximize the sum of sensitivity and specificity -1 at 0.49. It provides a balanced approach. We are not being too conservative or too aggressive. The graph shows how we increase the threshold, sensitivity decreases while specificity increases. Youngdan's index finds the optimal balance point. Note that the model generalized well to the test set with improved performance, suggesting robust learning without overfitting. The slide shows the critical trade-off in threshold selection. I tested 5 different thresholds ranging from 0.3 to 0.7 to understand their clinical implications. Low-end threshold like 0.3 to 0.4 catch most high-risk patients with sensitivity above 80%, but create many false alarms. Higher threshold like 0.6 to 0.7 reduce false positivity but dangerously miss many patients who need treatment. In breast cancer prognosis, false negativities are more costly than false positives. Missing a patient with poor prognosis could mean they don't receive necessary aggressive treatment with potentially life-threatening consequences. However, extremely low thresholds cause overtreatment. Our optimal threshold of 0.49 provides excellent balance with 77% sensitivity and 76% specificity on the test set. Clinicians might prefer slightly lower threshold around 0.4 to err on the side of caution, but 0.49 represents the statistical optimum from Youngdan's index. The confusion matrix shows 14 false negatives and 13 false positives, a nearly balanced error distribution. The precision recall curve is particularly useful when evaluating performance on the positive class, in our case, identifying patients with poor prognosis. Our model achieves an AUPRC of 0.7441, which is substantially better than the baseline of 0.5299. The baseline represents what we would expect from a no-scale classifier that randomly predicts based on class prevalence. The 40% improvement over baseline demonstrates that our neural network has learned meaningful patterns. The curves show the model maintains good precision across various recall levels, which means we can adjust the threshold to prioritize either precision or recall depending on clinical needs without dramatically sacrificing the other. At our optimal threshold of 0.49, we achieve 78.69% precision and 77.42% recoil. Both are strong values indicating reliable performance. This means when the model predicts poor prognosis is correct about 79% of the time, and it successfully identifies about 77 of all poor prognosis cases. Understanding why the model fails is important as understanding where it succeeds. Out, out of 117 test samples, 27 were misclassified, a 77% accuracy rate. The false positive are interesting. These patients had good outcomes despite the model predicting poor prognosis. Many had high-grade tumors and aggressive genomic features that typically indicate worse prognosis. The model may be over-relying on genomic signatures and missing protective factors like effective treatment response or other variable clinical characteristics not captured in our features. False negatives are concerning from a clinical perspective. These are the patients we missed who actually had poor outcomes. Their predicted probabilities were often close to the threshold, suggesting borderline cases. Their gene expression profiles may have appeared more favorable than typical poor prognosis cases, causing the model to underestimate risk. Several systematic issues emerge. First, there is sometimes a mismatch between genomic and clinical features. Second, we are working with only 20 gene expression features, which might not capture the full complexity of breast cancer breast cancer biology, missing important factors like lymph node status, treatment response, and comorbidities limit our sorry for the terms the term pronunciation that may not be correct. Comorbid comorbidities limit our predictive power. Finally, let me explain what PRC baseline represents because it is a common source of confusion. The baseline of 0.5299 represents the performance of a no-scale classifier essentially random guessing weighted by class prevalence. If we randomly labeled patients as poor prognosis, proportional to how common poor prognosis is in the population, we would expect to be correct about 53% of the time. Mathematically, this baseline equals exactly the proportion of positive class samples. For a balanced random classifier, the expected precision converges to the prevalence of the positive class. This is different from ROC curves, where the baseline is always 0.5 regardless of class imbalance. In our test case set, 62 out of 117 patients have poor prognosis, giving us 52.99% or 0.5299. This is our baseline, what random chance would achieve. our model's AUPRC of 0.7441 significantly exceeds this baseline, demonstrating that this neural network has learned meaningful patterns from the gene expression and clinical features. The 40% improvement over baseline is substantial and clinically meaningful. Now we move to the concordance index, which is specifically designed for survival analysis. Our test set shows a C-index of 0.713, an AUROC of 0.7724, a difference of about 0.06. The C-index evaluates 5,299 comparable pairs from our 117 test samples. A pair is comparable only if we can definitively determine which patient had worse outcomes. For example, if one patient had an event at time 5 and another was censored at time 10, they are comparable because we know the first had the event. But if a patient was censored at time 5 and another had an event at time 10, they are not comparable because we don't know what would have happened to the first patient. The key difference between AUROC and C-index is what pairs they consider. AUROC looks at O positive negative pairs, treating this as pure binary classification. That's 62 times 55 equals 3,410 pairs. C-index only uses comparable pairs from survival analysis perspective, 5,299 pairs in our data. This is why there are different denominators based on different assumptions. AUROC treat outcomes as binary regardless of time, while C-index respect the temporal ordering and sensory structure of our survival data. To validate our model's clinical utility, I created Kaplan-Meier survival curves stratifying patients by predicted risk using our optimal threshold. The curves shows clear visual separation between high-risk and low-risk groups. The high-risk group shows in red demonstrates significantly lower survival probability throughout the follow-up period compared to the low-risk group in blue. The separation appears early and persists over time, which is exactly what we want to see. The low-rank test confirms this difference is statistically significant with p less than 0.05. This is powerful clinical validation. It means our neural network model, despite being trained on cross-sectional data with gene expression and clinical features, successfully capture prognosis information that translates to actual survival differences. From clinical perspective, this stratification is invaluable for treatment planning. Physicians can use these risk predictions to decide on treatment intensity, more aggressive approaches for high-risk patients, potentially less intensive monitoring for low-risk patients. The clear separation validates that our model captures biological and clinically meaningful differences in clinical features, successfully capturing prognostic information that translate to actual survival differences. And this is a short summary of my homework assignment. Sorry for the voices. I'm currently in a cold right now. Thank you for patience and thank you for listening. Have a nice weekend.